Camera, hello.
Cartesian coordinate. I have quadrant 1, 2, 3, 4, so I'm going to label those for us. And I'm going to go ahead and put some letters up here that won't mean anything just yet, but as we progress, there will be something. These will be meaningful in a little bit. So up here I'm going to have A, S, T, C. Now, Sydney was kind of asking about how do we figure out all the points? I think the hardest part here are the points on the unit circle. Not only memorizing them, but seeing where they come from. So what we're going to do now is talk about, since you have your unit circle in front of you, Suraj, what are the 3 angles in degrees that we want to worry about in quadrant 1, between 0 and 90?
30, 45, and 60.
So we want to look at 30, 45, and 60. So I'm going to go ahead and draw those up here. Not going to measure them. We're just going to eyeball them. I'm not going to ask for... So we have our 30. Need that new board soon. Did you say 90 or 60, sir? Okay, I definitely mixed up what you said. All right. All right. So, if I have a circle there, is my red line from the center to the edge, my green line from the center to the circumference, and the purple going to be the same length? Why? The radius. And for the unit circle, what do we define the radius to be? 1. So I'm going to go ahead and make that note up here. All right. I can't hear you. That's a really good question. Let me ask you, well, let's look at the tool I used to draw the circle. Yep. No, circumference is equal to 2 pi times r. The radius, what's the definition? Let's do it this way. What's the definition of a circle? It's a collection of points that are the same distance from the center, right? So that's what the green line represents. If I center here and I go all the way around, this is uniformly the same distance no matter where I go from here to here, right? The way I drew this is I had this pivot point, and this is a fixed position, and when I stick the marker in, the length in this is never changing between here and here, right? So as it goes around, it doesn't generate any, it can only generate a circle. So like, let's say,
like if we're trying to find the radius of the triangle, but the triangle isn't starting in origin.
ooh, okay, that's a really good, did you hear her question? What if we're trying to find the radius of a triangle if it's not at the origin? Does a triangle have a radius? No. In a right triangle, it's a hypotenuse. So the reason this works is what we're saying is we're going to take a circle on a coordinate plane, and we're going to build right triangles by starting at the center and going up to here, and then dropping an altitude from here to here. Because I am doing it this way, since my red, green, and purple line are all 1 unit long, right? What is going to change on my triangles? Not the hypotenuse, but the x and the y value, right? Like this right here is much shorter than this one and this one. As this one's shorter, what's happening here? It's longer. So there's definitely some sort of relationship that we're establishing. Now, we kind of got to this, I don't remember whether or not, the 30, 60, 90, 30, do we talk about these too much or at all? Nope. That's where we're going to start building these from. So I'm going to get rid of this from last class. Yeah, Siraj, grab a picture while I find an eraser. And if you had me for geometry, I told you, do not forget these triangles. Obviously, you're going to forget these triangles. But I did tell you they won't be on the EOC, so that you probably definitely forgot these triangles. So we're going to do them again. But, okay, let me ask you this. Do you see a relationship between my red, green, and purple angle and these 3 triangles that I've written on the board? What do you see? Yeah, exactly. I can pick this triangle up, and if I put it here, it'll make my red triangle, right? If I pick this one up, it'll make my green line. And if I pick this one up and move it over, it'll make my purple line. The reason I said it was so important
is because the 30 and the 60-degree angle, they make the 30, 60, 90.
Perfect. So,
and the 45 makes the 45.
So I have all 3 special triangles on my unit circle now.
Yeah.
Now the reason I'm doing that is, let's start with the 30, 60, 90. Does anybody remember the relationship of the sides for a 30, 60, 90? So what side, opposite of which angle will be my shortest side?
The 30.
I swore I would never do this again now that I don't teach geometry. Do this for me real quick. Do this, right? What's the measure between your hands right now in angle? 0, right? Open it 30 degrees. What's happening? So look at the distance between your fingers, right? Now go 60 degrees. What happened to that length when I went from 30 to 60? We got longer, right? So the smaller the angle is, the smaller the opposite side, right? So which is the smallest angle? So what's going to be opposite of that? The smallest side, right? So what I'm going to do is I'm going to call this S for smallest side. And now I want to see if I can find a rule for the 30, 60, 90 that I can use for all 30, 60, 90s. Because if something falls out of this, then we can kind of apply it everywhere if we see a pattern emerging. So I'm going to do my first one. This one will not be a triangle to be used for the unit circle. What does that mean? My hypotenuse might be something else. Would that make a unit circle if my hypotenuse is 2? No, right? Because the radius isn't 1. But if I do this, and this one I'm going to cheat a little bit because I have the knowledge, but then we're going to check it when we're done. Opposite of 90, is that going to be my middle length or my longest length? Longest, right? I'm going to tell you this. If my shortest side is S, opposite of 90 is always 2S. Whatever S is, I just multiply it by 2. I've got my longest side. Here's the oddball. Whatever my S is, if I multiply it by the square root of 3, I have my other side. That's how we're going to prove that we're right. But what I'm showing you is if you see 30, 60, 90 as your 3 angles, don't do the Pythagorean theorem. Just look at one of these sides and you can find the other 2 like that. And then I heard someone say, I'll never be able to memorize this circle. If you remember these rules, it's going to give you your coordinates. Once you know your 3 coordinates here, you can go back to geometry, use your rules of reflection, and you're actually just, well, done. So Joey, if my longest side is 2s, right? If I want to solve for my shortest side, what would I do? Yeah, perfect. So what would I get? 1. Now, how did Joey know that? How did you know that, Joey? Yeah, well, let's put it that way. If I divide by 2, s is equal to x over 2, and I know that that is a relationship between here and here, so I put 2 here and I get 1. Kind of a sloppy way to do it, but it's one way just to see that thought process. The side opposite of 30 will always be 1/2 of the length of the side opposite of 90. I promise it all ties together. I promise. Okay, the reason I'm doing this now, first, this is your first time in my class. I always say never listen to a math teacher that doesn't show you at least 3 examples if they're trying to prove a point. So I can't keep using 1 because these are set relationships, and if I put 1 here, I have nowhere else to go. So I'm showing you like a different case. I'm not even talking about the unit circle, but if I pick this up, this would coincide with this red triangle, right? But the hypotenuse would be twice as long. So what we're going to do is slowly shrink this down to a length of 1. And then it's going to be relevant. But I can't just tell you this. It would be wrong to just say, take this and never show you why it works. But I want to show you more than once. But I can't show you more than once with a unit circle because it's just set in stone. So what does my s equal to here, guys? 1, right? So what do you think the side right here opposite of 60 is going to be? Mo, what are you going to give me for opposite of 60 now? Well, what is s, Mo? So what's s here? 1. What's 1 times the square root of 3? All right. Now, who asked about the Pythagorean Theorem a second ago? Perfect. Plug this into the Pythagorean Theorem and tell me what you get. Is this true, that a squared plus b squared equals c squared? It is, isn't it? Kind of crazy, right? All right. Now, can I get away with just showing you 2 examples before we move on? Suraj, go for it.
Why did you do all of that on your...
Show you every step of the Pythagorean Theorem. I'm verifying that these 3 sides work.
Oh, okay.
I heard my name was... Somebody said Mr. Fimble. Oh, what's up? Oh, that's the part in here. All right. How would these relationships change on the sides here if I change the 30 and the 60 in this triangle? Or if I find an eraser. Okay. How are these ratios, are these side lengths going to change now? They're in different spots, right? But the relationship tells me what they have to be when they're across from each other. Kaylee, what's going to happen? Okay, I have. Oh wait, I need to put 2 here. Sorry, I skipped. Thank you. So what's going to happen now? Yeah, my A and my B swap. Okay? So, now I've given you 2 examples. You can verify that still works, right? There's 2. Let me go to my 3rd example and then my 4th example. All right. This is all I'm going to give you for now. I just want to ask you, if I move this triangle into my coordinate plane over here, would this point be on the circumference of my circle? Why? Perfect. The radius is 1 and the hypotenuse, even though it's not there yet, represents that. Now, if I make this a 30, 60, 90, this is going to change, but not by too much, right? Opposite of 90 is still 1. So I can take 2s is equal to 1. Okay, so if I look at 90, the side opposite of 90 is twice the length of the smallest side. Not even that yet. I'm just looking at what C actually is. And I'm saying 2 times S, which is my smallest side, has to be equal to 1. So opposite of 90 is 2S. Now that I know it's equal to 1, I can set them equal to solve for S. So what is that going to be, Kaylee? So where does that go on my triangle? Yeah, why does it go opposite of 30? Because opposite of 30 is whatever S is actually equal to. And then Callie, what's going to go opposite of 60? Won't be 1/2. Won't be 2. On this triangle, opposite of 60.
Oh, is that the same thing as the last?
Say it again, Maddie.
1/2 square root of 3.
Yeah. Opposite of 60, we take whatever S is. Now, Maddie, I'm going to say I did not think you had a shot at that. So, talking about Andrew or the game and stuff over there, you still caught on. That's pretty good. That's pretty good. Never change. Always, if it's an irrational number, leave it like this. I want exact answers. Can we slightly modify this? If I do 1/2 times the square root of 3, isn't that the equivalent? You took the words out of my mouth. Yes. Is that not this point right here? Square root of 3 over 2. I don't know, is it? That's weird, right? Kaylee, why did you see that so fast? So you recognize the numbers, and you say, oh wait, that fits into that hole right there, right? Now, pretend this was on a graph. Isn't this my x value? Isn't this my y value? Don't I write a coordinate as x comma y? So that's how the unit circle works. Now, here's one that comes out of this for free. If I swap this position, don't these two just swap? Let's see it. 30 here. 1. We know opposite of 60, or opposite of 30 is half of whatever that is. And then this is just square root of 3 over 2. So, when I have my 60 in purple here, what's this coordinate? Do we all agree with Sydney? Yeah. Gotta stop with the... All right. Yes. No, which is what? Like, how did I know to put half here on this one and half here on that one? So, how did I say it? Guys, let me say it again. Are you saying how did I combine these, or how did I get the point? How did I get to them? So when I solved for this, right, I didn't have the plane here yet. I just found the lengths of these, right? I knew that this was going to be square root of 3 over 2, and this is 1/2, just by solving for the triangle. Now, I added the coordinate plane, and I said, let's put this in standard position where this vertex coincides with 0, 0. And basically, this is just saying that the length of this from here to here, according to the Pythagorean Theorem, is that length, right? And I did the same here. From here, if it was actually on the plane, to here is 1/2 of the unit of the length of the radius. Now, if this is on a coordinate plane, this could be represented as 0, 0, and this could be represented as, right? And then here, this would be the x value, comma the y value. So I'm just taking the lengths of each side. So the side opposite of 60 has this length, the side opposite of 30 has this length. That means the coordinate for the top right corner of the triangle has to be at the point where those two meet. Now, hold on, I'm going to go Kaylee, then Mo, but ask any more questions you have before we move on. Are you saying how did I find the values? So for this, if I know my length is always going to be 1 in the unit circle, right? I know that the side opposite of 90 is my radius, and that's its value. I know the longest side is always twice the length of my shortest side. So I just take this radius, divide it by 2, which gives me 1/2, right? And once I establish what the shortest side is, whatever that number is, I take the shortest side times the square root of 3, and that gives me the third side. And this works for any numbers. As long as I give you one number, you can find the other two, and then you can verify it by putting it through the Pythagorean Theorem. I'm going to do it again with the 45, 45, 90, but I want to make one more point after I answer Kaylee and Mo's questions. So Kaylee, go ahead.
Will you ever have to, if it's not a special case, for this chapter, are you going to use the hypotenuse of one of the special?
Are you saying like if I told you that this angle was 22.5, would you ever have to find it?
No,
Okay, thank you.
if the angle is 45, would you use the hypotenuse to, but it's a different angle, for the,
Ooh.
it's not 90, it's more than,
So you're saying down here would be different, like this is 105? Here's the great thing about right triangle trigonometry. We're not going to do anything with it unless it's a right triangle. So we only are going to worry about right triangles right now, and we're only going to worry about these special cases. Mo. Mm-hmm. Mm-hmm.
It says, like, for example, sine is y.
Yes, sir.
Y over y.
Yep.
Which would mean the hypotenuse of the radius is 1.
Yes.
But that also implies that the opposite is y. That would change if we had theta at the top. How would you share that down?
Beautiful question. All right, Mo, let me make sure I'm interpreting your question right. I'm only talked about if we're talking about theta being here, right? Well, no, that's all I've said so far. But your question is, what if somehow it ended up here, right?
Yeah.
Here's the best part. When we deal with the unit circle, when we put it in standard position, the only angle we care about is that point that originates from the origin. So we're considering them only in this direction when we find our side lengths. Now, Mo, something interesting, this just leads to my next thing. Do you see how these two are just the transposition of these two? They just swap, right? When I did my 30, 60, 90, and I swapped them, didn't these values just swap? So, if I put theta here this time, right, this would give me this result, wouldn't it? Well, my y is 1/2, right? And then I have square root of 3 over 2. This triangle, these are both solutions to the Pythagorean theorem, right? If I square these and add them together, what am I going to get? I'll get 3/4 plus 1/4, right? 3/4 plus 1/4. So if theta's here, this is the right angle, but now I've rotated everything. So we're never going to deal with theta up here. We always want to make our central angle at the origin or in standard position. But what you're saying is, if we did consider them that way, that's kind of the same as just taking this triangle, rotating it so my 60 is here now, isn't it? So that's why we're still talking about this one. That's why these are transposed. If I flip the order, if I move theta to here, then they flip. But that's just this triangle rotated up. Well, no, not, it's rotated up, then reflected down, right? And what do we know about rigid motions from geometry? We never talked about them in this class. Rigid motions preserve side and angle length. What are our rigid motions? Translations, rotations, reflections. And since all I've said is let's rotate this up and then reflect it down, they're going to be the same. So you're saying, could we just use this to solve the same? Yeah. But we want to make sure that this, and this are solutions to both the circle and the Pythagorean theorem so that we know they intersect. All right. So that's why these two flip. So, Sydney, that's part of my clue there. If you can just remember this one and this one, you know that these two are transposed. But I know you said the hard part was remembering that one. Isn't that what you told me? No. Which one did you say? Oh, that's the easy one? This was the hard one. Yeah. And this one. Just the flip now. So at least we took 33% of the problem away. Anybody know what that's going to be? Sydney, what is it going to be?
It's 2 squared over 2, 2 squared over 2.
Now, this kind of might cause a fight in here. What if I said I don't agree with Sydney? Does that make her wrong because I don't agree with her? Absolutely not. Wait, what? I would put it as this. Are those equivalent?
Yeah.
Mo, why are they equivalent? Yep. Is Fimble ever going to do that? No. If I won't do it, am I going to ask you to do it? Square root of 2 over the square root of 4. What I want to say is, Sydney is correct. I'm also correct. Most of you probably have Sydney's answer. Some of you may go home and look it up and see my answer. I don't want you to get home and be frustrated that you can't figure out why our answers are different. These are equivalent. Both are perfectly acceptable. Again, this is better before calculators. This is fine with calculators. I'd rather divide an irrational number by a whole number than an irrational number by a whole number. This is like Sydney's special project. This is going to take years to do by hand. This won't take very long to get a good approximation. Now, can I prove to you that those are the right answers by using, well, what kind of special triangle do we have here? In my green, this is 45 degrees. That's 90 degrees. What does that have to be? Josh, you remember that one? Yeah, exactly that. So let's bring that over here. Jeez, these are just getting worse. All right, Josh, you answered my last question. Pick somebody for me. Anirudh. Josh, why are you doing these favors? Right, he was fishing for... I know. Anirudh, what kind of... besides being a right triangle, what kind of triangle is this?
It's a 45, 45, 90. Right?
That was given, though. What else can you tell me that I haven't told you yet?
Both of the length of the triangle.
That's the word we're looking for. Now, that's a word I don't really spell well, so I'm going to write it like this. That may even be wrong. I think it's C-E-L-E-S after that, but if it's an isosceles, what do I know about the two legs? They're the same. Perfect. This is where it gets a little weird. Anirudh, pick somebody.
Oh, Josh. Or Joey.
All right, any of the three of you can answer this question. If I want to Pretend that I picked up this 45, 45, 90 and put it here. What is the length of the hypotenuse?
S times the square root of
Dang, you're way ahead of me on that. He's giving me the answer. But Joey, just what's the length of it? From this triangle right here, from center to here, how long would I have? 1, perfect. So, how in the world would I figure out what these two sides are? They're equivalent, so I can use the same variable, S for sides. You did the opposite of the Anirudh. Every time I look at you, your eyes go straight back to the TV. So, can I use the Pythagorean Theorem to solve for any right triangle? Okay, what would my A value be? Oh, we want to only work with side lengths in this. So it's just S is A, B, and C, right? So I would have S squared plus S squared. And what is that going to be equal to? I am looking right at you. You made eye contact, then you darted. What is my hypotenuse's length? I still am talking to you. No matter how awkward you want to make it, we'll finish this one off. What is my hypotenuse, right? That's what this side represents. Yeah, it's 1. So I'm going to have 1 squared. All right, now the last thing I have for you is just pick the next person. Josh, you cannot hide your head in the sand, man. Every time she turned her head, you know. Who is it? Addison. What would you do with this? Just can we simplify the left-hand side? Well, are these bases the same? Yeah. Are the exponents the same? Yeah. So then we can add these together. What would I get? Perfect. Pick the next person to answer my question for me. Callie, what's next? I'm trying to solve for S. And how do I do that?
You do it however you want to do it.
Well, what's your step? I agree with you. There's two things we can do.
Do something with the 1 maybe.
Yeah, what would you do with the 1?
Simplify it.
By doing? What is this simplify? Okay, what would it become? There you go. Callie, pick somebody. I forgot what my question was going to be. So, Katie, you get a free pass on that one. Katie, pick somebody. Who? Maddie. I heard Matthew. I was like, I don't. What would I do now, Maddie? I'm going to get this by itself. Thank you. Because we got to get the S alone first. Now it's square root both sides. And I'm going to just make one question for you guys. Can I break, what's the square root of 1? I'm going to go ahead and evaluate that. But I can't evaluate that. All right, now whose answer is right? Sydney, mine or yours? No, it's not. We just simplify it to yours now, right? We got my answer out of it. But yours is the same. So I'm just stressing the point that neither one of them is right or wrong. They're equivalent. And let's try and show that that's true. Anirudh, you told me this was an isosceles and they had to be equal. Is that okay to write them like that?
Yes.
Why?
Because they're the same.
Perfect. Plug it into the Pythagorean theorem real quick. Tell me what you get. We need less than a minute for this one. And then we're going to work on how all the rest of this falls out. Yes.
So this is like the 45, 45, 90. What would I put for under the 90?
S times the square root of 2. Thank you for S. Square root of 2. Right? Because look here, Suraj, this is 1. This is, ooh. Yeah. Why does this feel wrong all of a sudden now that you've asked me? Like I knew it so, it's. No, it's right. That's square root of 2. It's that. And the way I did it here is I just did 6 squared plus 6 squared and factored it down to that. 6 is my s, square root of 2. Kaylee, if you want, is that the staple? That's not going to work, right? Go in my top left drawer and get a full stapler, not the one I accidentally broke. Give me 1 second, sir. What's up? Yes, sir. Arnie, were you calling for him to go? Oh, okay. All right, guys, did that work? Say that again?
Which test are we doing tomorrow? One of the all the
The one I'm going to show you in a few minutes. I'm going to show it to you so there's no confusion. If I try and explain it, it's just going to make things more confusion since visually you want to see it, right? Now, really quick, if I ask you for the sine of theta here, this is going to be opposite over hypotenuse. So Suraj, how do I find sine? I look at the opposite and the hypotenuse, right? Sine of theta. If I'm going back to the trig, right? All right, let me get this last part in, then we can fill out the rest of this really fast. So, Suraj, what's my y value on this triangle from here to here? And what's my x? All right. Now, Suraj, what's my y value? And what's my radius? My radius. So I could rewrite this as, right? Because my y coordinate is 1/2 length and a 1 length, right? What is 1/2 divided by 1? And that's why I can say sine is equal to 1. I can do the same for cosine. X is square root of 3 over 2. Hypotenuse is 1. Got that. What is the quotient? Who answered my last question? I don't remember. We're going to run out of time to look at the quiz. Joey, pick somebody for me, sir. But Suraj is like the only person engaged right now. Suraj, pick somebody that's talking right now, not paying attention. Who? Andrew! What is my quotient identity for a tangent? What does tangent equal as an expression of trigonometric functions? That's as it is on a coordinate plane, but I can also say it's equal to sine over cosine. That is the right answer, though. I know. He's thinking ahead. Now, I don't want to explore that too much right now because I want to get through this, but this is why we can say sine is equal to y, cosine is equal to x. This one's a little bit different. You just take the opposite. You're always going to take your y value, divide it by your x value. All right, so now we run into this problem. These are not going to be nearly as nice as the other ones. Whoa, way off there, buddy. All right. Here's the easiest way to remember the next angle. What is this angle right here? It's a right angle, right? Plus how much more? So this one is 120. You just take these and add, how much in the quadrant? 90. All this is the quadrant shifted 30 degrees. So you're going to take whatever this is and add 90 each time. So what's the next one going to be? And what's the last one going to be? 150? Now, there's a difference from 0 to 30 of 30. from 90 to 120, difference of 30. 90 to 135, difference of 45. All of these are creating right angles. So you just keep adding 90 to get the values in the other quadrants. So your homework is find these three in degrees. Also, does anybody remember from geometry, and then after that, we got one other thing to do, and then we'll start looking at the quiz. Does anybody remember from geometry the rules to rotate something 90 degrees? And, all right, Mo's giving me this sign. He's not choking, so let's see if we can. Mo, if I gave you x comma y, my interpretation is to do y comma x, right? Is there anything else to do, though? Negative, right? You change the order of the coordinates, and then you negate the one that used to be y. If you remember this rule and these three coordinates, you can generate all these. So this here means change the order. This will be 1/2 square root of 3 over 2, and then make that negative. Now, does that make sense? Isn't this negative along the x, but positive along the y? And as long as you just know these three, Sydney, this is what I was going to tell you. You just follow this rule. Change their order and negate it. And then I can do it again. If I change the order, it goes back to negative 3/2. Well, I'm negating it already. Oh, minus 1/2. And that makes sense, right? So your homework is to also find the coordinates of the rest of these. And what's the rule for doing 180? You flip and negate, right? 1, 0 becomes negative 1, 0. Isn't that exactly? So now, I put this at the very beginning of class, and I said this is where we're going to end. ASTC, all right? I'm going to tell you the mnemonic device. This is all seniors take calculus. In sorry. In quadrant 1, all trigonometric functions are positive for their coordinates. In quadrant 2, only sine is positive. All right, if I look at the opposite over the hypotenuse. Here, my y is positive, but my x is negative. And here, it's positive. So opposite over hypotenuse has to be positive. Here, only tangent is positive. That's the oddball, so everything's going to be negative. But tangent's opposite over adjacent, so if I take two negatives and divide them, I get a positive, right? So then tangent's the only time. And then here, cosine, that's my x. Going in this direction is positive, but going down is negative, but it doesn't matter. I'm not looking at y at all for cosine. The hypotenuse still is traveling in a positive direction. So in quadrant 1, all trig functions are positive. Sine's positive in 2, tangent's positive in 3, and in quadrant 4, only cosine is. And the last thing for your homework is to find all of the radian measure. But you can convert this to radians, this to radians, this to radians, and then just add pi halves instead of 90. And this is your homework for tonight.